Okay, so this is STEP support assignment number 20. It's our second assignment that's based on the Fibonacci sequence. So yeah, this should be, I mean, it's not fun, but let's go into it anyway. So f of 0 is 0, f of 1 is 1. This is the recurrence relation, just writing down what they've been in the question. Show that this is this and this is true, and then compute this. If you're given show that, you need to do this super overtly and carefully and display everything, all of your working, right? So what you're saying is, if n is 1, then this term becomes f of 1 plus 1, this becomes a 1, this becomes a 1, and you get f of 2 as 1 plus 0. And then you substitute in the values that you know. You know f of 0 is 0 and f of 1 is 1, so f of 2 is 1. Like, this is the kind of thing you want to do if it says show that. And essentially at this point, I'm just going to repeat that over and over. I'm going to say n is 2, that becomes a 2 plus 1, that's a 2, that's a 2 minus 1, that becomes that. I know what these two things are because one of them I just worked out, the other one I was given, and let's have f of 2 as 3. And I'm just going to do this over and over again, right? So they're just really formalizing, you know, you learned Fibonacci maybe in year 9 or whatever, but they're just really heavily formalizing all the notation, because when you get to like university maths, you work with notation like this and work with this amount of care rather than just being like, oh yeah, you just add up the two numbers before it, mate. And that's the whole thing. So we're just taking real care of this, and I think we're almost done. And we arrive at f of 7, and those are all of our terms. Okay, compute this thing. So f of n plus 1, f of n minus 1, minus f of n squared for a few values of n. Okay, so I'm computing this for different values of n. So I'll put the working here, and then I'll put the result here. So hopefully this will make sense in a second. If you put in n is 1, you get 1 plus 1 is 2, 1 minus 1 is 0, 1, 1. But I know what these are because I have my little table. So f of 2 is 1, f of 0 is 0, f of 1 is 1. So this becomes 0 times 2, or sorry, 1 times 0 minus 1 squared. Now, this isn't negative 1 all squared. This is just minus a 1 squared. 1 squared is 1, and then it's just minus 1. Okay, so that's minus 1. What about for n is 2? Well, again, just put n is 2 in here. You get f of 3, f of 1 minus f squared of 2. Again, read your table, 2 times 1 minus 1 squared, and that turns out to be 1, I think. N is 3. Same kind of idea, put your things in, check my maths here, but I think I get minus 1. And n is 4, again, same idea, check my maths, I think I get 1. Well, this is a pattern, right? So that's good, because to guess a general formula, I'd probably need a pattern. So I'm going to guess that the formula for this is minus 1 to the power n. Because notice, if I use an odd number for n, I get a minus 1, and minus 1 to the power of something odd is minus 1. But if I use an even number, I get positive 1, and minus 1 to an even is a positive. So I'm going to guess that's my formula. And now, prove it by induction or otherwise. I mean, you probably don't want to do the otherwise thing unless you're just here to flex. So let's do induction instead. So yeah, prove this by induction. Now, hopefully you've seen lots of induction in maths. The first step is to prove it's true for a particular value. Now, on the previous slide, I proved this was true for, I think, like 4 of them. So I don't need to do this. Again, assume that it's true for n is k. So I'm going to put n is k into these and assume that this is true. I'm just going to say this is true now. That's true. And now I need to show that it's true for n is k plus 1. So now I need to prove this. So replacing all those n's here with k plus 1s. Now, this simplifies a bit immediately into that. K plus 2, that's just a k, and I have this. Right? So this is what I'm trying to prove, and I'm assuming, and I can use this whenever I want, because I've assumed it to be true. So I'm proving this, I can use this whenever I want. Okay, so this is the thing I'm proving. I can assume this whenever I want. This thing here is just this side, and I'm going to work this side into this side. Okay, now I've highlighted the fk plus 2 because I just have a Fibonacci relation that I can use to get rid of that. I can just say that's the previous 2 terms added up. So I can get rid of that into that. Okay, so that's good. The reason that I thought to get rid of that, by the way, is because at some point I know I'm going to have to use the assumed thing. And the assumed thing doesn't have any k plus 2s in it. So getting rid of that and lowering them down seems like a really good idea. So okay, well, I've put that in there now, I can expand out. And now this took me absolutely forever to work out. I tried so many things before I realized just how hard the people at Cambridge were messing with us when they made this question. Because, you know, you can try and replace this with this, or this with this, or both of them, or either of them. You can even try replacing this, and it never quite works out. what you need to do is you do need to replace this with the two terms below it. But this is an fk plus 1 squared, so there's two of them. It's fk plus 1 times fk plus 1. And the trick here is you only replace one of them, and you leave the other one. So this used to be fk plus 1 times fk plus 1. I've replaced one of them using my recurrence relation and kept the other one. Dear God, did that take me a long time to see. Anyway, then you expand out. fk plus 1, fk minus 1, fk plus 1. This term cancels with this term, which is lovely, and I'm just left with the fk squared minus these two, which is great, because look how close that is to the thing that I've assumed. And I know whenever you're doing induction, at some point you need to use the assumed fact, really. So this is really close to the assumed fact, right? All that's wrong about it, so I started here, I've worked my way to here. All that's wrong about this is the signs are the wrong way around. But that's fine, right? Because if I times all of this by minus 1, I'd make the signs be this way, and that would just be a minus 1 to the k. So now I've got from here to here, which is great. Just be careful here, this is a minus 1 times this stuff. But minus 1 I can write as minus 1 to the 1 times this. And of course, same base now, add to the powers for a minus k plus 1. Sorry, minus 1 to the k plus 1, which is what I was trying to prove. So I'm done here. But yeah, that spot in the middle there, if only replacing one of them was really tricky. Okay, part 3 then. By induction on k, or otherwise, again, you're probably going to do this bit, show that this is true. Now, let's just take a minute to appreciate what this formula is. What this is saying is if you have two numbers now, two random numbers, this is a formula for breaking those two numbers apart and just finding the Fibonacci term for each of them. So maybe this is an easier example. If you had n is 10 and k is 5, instead of having to compute all the way to f of 15, instead of having to go to the 15th term, you can just do f of the 10th term times f of the 6th term plus f of the 9th term times f of the 5th term, right? So you don't have to compute as far, right? You can hold back and only compute certain things. So again, if this was 20 and this was 30, you don't have to go all the way to f of 50. You just have to go around 20 and 30 and then multiply a few things together, which is probably much easier. So this is a really neat little formula if it's true, because it saves you computing, if you wanted to compute large values, saves you computing much further because you can just compute smaller values, times them together and add them together. So if this was true, it would be pretty cool if you were actually interested in finding lots of Fibonacci values. Okay, so now that we've talked about that this is a thing that just breaks apart two numbers into two separate Fibonacci terms, let's prove this with induction then. So first step, like we said, is to show that it's true for k is equal to 1. So let's put k as 1 into here. So I'm just replacing those k's with 1s. Just all those k's go into 1s, that becomes a 0 then, doesn't it? That's just an f of n plus 1. Now f of 1 is 1 and f of 0 is 0. So that's just fn plus 1 equals 1 times this plus nothing. So it's just this is equal to this. So that's good, I'm done. So I've shown that it's true for k is 1. Next step, of course, is to assume it's true for k as m. So I'm going to put an m in here instead. So every time I see a k, I'm going to put an m in. So that's the assumed fact. That's the thing that I can use whenever I want. And now, so that's the thing I've assumed, I can use that whenever I want. And now I'm going to prove that it's true for k as m plus 1. Now I'm going to put m plus 1 in here, obviously, because that's the thing I'm trying to prove. And I end up with this. Okay, and notice how that would just be an m, but I'm leaving it like this just to show you where I put that m plus 1 in, replaced with the k. Okay, so now I'm trying to prove this. So let's start with this side here. And now, be careful here. I don't have any rule for this, except for I can just use the regular recurrence relation, right? I can say that's equal to the term below it, 1 less than this number, which is n plus m, and then the term below that, which is this one here. Again, 1 lower. Now I've highlighted this red because I have a fact for this. I have the assumed fact. So I can replace this with this thing here. So I replace that. Now, this is a problem, and you need to be super careful here, because I can't really do anything to this. It's tempting to try and use this fact here. Like you could say, oh, well, is this not just n plus m minus 1, and then I could just replace these with m minus 1s. But that's not how induction works, right? Like I've only assumed it's true for k is m. I haven't assumed it's true for any other values. And if I was just going to replace this with an m minus 1 and put it in here, well, why am I bothering this at all? Like, going through the effort of proving it's true for m plus 1, but then just replacing this with an m minus 1 just because I feel like it. That's not okay. I've only assumed it's true for this, so this is the only thing I can use. So I can't break this apart using anything because I don't have a rule for it. I only have a rule for that. Okay? So I can't do anything else. I mean, the thing that I could do, I could try doing some of this, right? Like I could just try breaking it out into the two lower terms, but then I just end up with an m plus n minus 2 and an f of m plus n minus 3, and that doesn't seem very helpful. So I'm stuck. And what I have to do is I have to go back to the start and do stuff a little bit better. So let's go back to the start of this question, doing induction on this. So I'm just trying to prove this. Now the first step, like I said, is to show that it's true for n is k. Sorry, for k is 1. So I'm going to put k as 1 into here, and this is just the same as what I just did. It turns out to be 1 lot of that and 0 lots of that, so you just get this. So that's good. But now I'm going to do part 1b. Now I'm going to show it's true for k is 2. Sorry, I keep speaking. K is 2. When I put k as 2 into here, I get this. Now f of 2 is 1, f of 1 is 1, so I get just this plus this, but I know this is true. Because that's just how Fibonacci works, right? So I've proved it's true for k is 2 now and k is 1. And now what that means I can do is I can say, well, now I'm going to assume it's true for k equals m using this case as my kind of basis for that assumption. I can show that it's true for k as m, which gives me this assumption, which I can use whenever I like, just putting m into here. But also, since I have another value that's 1 lower than the one that I just used, I can now also, part 2b, assume that it's true for k is m minus 1. And I'm using this as my basis now for that, because I'm using this for my k as m, and I've got a value that's 1 less that I know is true, so I can now use this as the basis for this assumption. And now look, now I have a rule that breaks up that m plus m minus 1. I have this rule, right? Just replacing the k's with m minus 1s. Okay, so now I'm going to go back to this, and I've got these two assumptions, and I'm going to still try and prove this case here. Okay? So I'm going to start on this side, and I'm going to do the same start. I'm going to break that down. I don't have a rule for n plus m plus 1. I only have a rule for these two things. So the only thing I can do here is break that down using the Fibonacci sequence principle of just it's the term below and the term below that. But now I have assumed rules on both of these things. So I can replace both of these things with my assumptions, which is great. So I can break apart these m and m's, both of them, into just m's and m's alone, right? Okay, so now what do I do? Well, let's look at the thing that I'm trying to get. I'm trying to get to this. Now, notice this is just an f of m, but that doesn't really matter. What I can see here is that my n's are good. I've got n plus 1, n plus 1, n. I like those. I want to keep those, right? Because they're in my final thing. Now the m's, the m minus 2, m minus 1, m minus 1, m, they're not so good. I don't want those. I certainly don't want stuff like this. That's nowhere in here. So the idea I'm gonna have is, well, let's keep the stuff that I can see, and try and make steps to lose the stuff that I can't. So how am I going to do that? Well, first I'm going to factorize the good stuff. So I'm going to factorize the things I like, the fn plus 1s and the fm's. I'm going to group those out. So here I've got fn plus 1 into f of m plus f of m minus 1. Those are the things that multiply this guy, right? And now I've also got f of n into this guy and this guy here. And now it might be clear to see how I'm going to get rid of these things that I don't like. I'm going to do it by using the recurrence formula, just the basic Fibonacci thing, that it's the term plus equals the term before it plus the term before that. So now I can replace this just using the Fibonacci formula with f of m, and this, again using the Fibonacci formula, but in a little bit more complicated way with f of m plus 1, because that's equal to the two terms below it, and this one, two terms below that. But now let's look at this and this. I think I'm done, because as I've said, this whole thing there, that's just f of m. Minus 1 plus 1 is nothing, so that's just f of m. So I think I'm done. And the entire question is done as well. So there were really only two really painful things about that question. Noticing that you have to use two cases for your proof by induction, that was really important in this question. And also in part 2, that bit where you had to use only one of the things and get rid of and keep the other one, that was tough as well.